Hello again. Now we will start the chapter Modern Physics. In this session, we'll discuss free electrons and see how they play a vital role in certain behaviors shown by metals. So let's start by discussing what free electrons are. Now, we have already talked about this in the chapter of electricity. We know that in metals especially, there are certain electrons which are relatively free from the atom in which they were, which means they are electrons from the valence shell which are now independent of the nucleus. So what these electrons do is they stay in that substance but they move freely. The motion of free electrons is compared to the motion of particles in a gas. Now you can imagine how the particles of a gas move. They move randomly and freely in every direction. Same is the case with free electrons. Now, due to this behavior, metals have a luster. Now, if you know that the classification of metals and non-metals was based on whether or not a substance has a shine. Now, the shine that the metals have is again due to these free electrons because they absorb and then re-emit light, which gives a specific luster to the substance that contains free electrons. Now, these free electrons are free to move inside the substance, but they are not free to eject from the surface. So let's say if this represents a piece of metal, then any free electron can freely move inside this metal in any given random path. But this electron cannot come out of the surface of this block. Right? So, and this is because if the electron leaves that surface, let's imagine a situation where this electron leaves this metal block. Then, if you think about it, on losing a negative charge, this block will gain a positive charge. And as soon as it gains a positive charge, it will attract the electron back. So, the electron is free to move as long as the neutrality of this block or that substance is maintained. So, to eject an electron from the metal, a certain amount of energy is required. The minimum amount which is required, the minimum amount of energy required to remove a free electron, from metal surface is called the work function of that metal. Now pay close attention to this definition. First of all, pay attention to the statement removing a free electron. Please do not confuse this with removing an electron from its valence shell. That energy, if you remember, is called the ionization energy. I'm sure you've read about this in chemistry. The amount of energy that you need to remove an electron from its valence shell is called ionization energy. Now that is not the energy which we are talking about. We are talking about free electrons which are already out of their valence shell. So these electrons are out of their valence shell and now moving through the substance freely. But as we have already discussed, they are not free to eject out of the surface. Now, the minimum energy that is needed to eject these electrons out of the surface which means we want to remove this electron from this substance. This minimum energy that would be needed in doing so is called the work function. And work function is defined for a material. Since we are talking about metals, we could say that work function is defined for a specific metal. And work functions are usually expressed in a unit which is called electron volt. Now 1 electron volt is basically equal to 1.6 into 10 raised to minus 19 joules. So this is the conversion between an electron volt and joules. And the work function of metals is usually in the range of a few electron volts. Right. Now that we understand work function, let's look at a few phenomena. The first of which is thermionic emission. Now, thermionic emission refers to emission of electrons when a metal is heated. So, if you heat a metal to very high temperatures, then recall that in heat we had studied that heat is nothing but disorganized kinetic energy. So, if you heat a substance, then everything that is inside that substance will start vibrating at a higher pace. Now when this happens, these free electrons also start to move faster than they were moving before. So if they gain higher speeds, it is possible for the electron to jump out of the surface. If you think about it, the requirement to eject the electron is basically energy. So if you give it additional energy, it might have enough energy to eject itself out of the surface. For example, say that a metal X has work function of 16 electron volts, which basically means that you have to supply 16 electron volts to eject an electron. Let's first see how much this value is if we calculate it in joules. So to convert electron volt into joules, we should multiply this value with 1.6 into 10 raised to minus 19. So this gives you 24.6 into 10 raised to power minus 19 joules. This would be 25.6. Now, this value is the amount of energy that is needed to remove this electron. Now, this energy can come from anywhere. In this case, it is coming from heating of the substance. When we heat that substance, everything starts vibrating at a greater pace. And hence, if you think about it, energy of every particle is increasing. So, even the electrons, the free electrons, they are getting additional kinetic energy. So, at a point when the free electrons get this much kinetic energy, they will easily jump out of the surface. And so, if you heat metals to a very high temperatures, they start emitting electrons. And you would later see that this property has variety of applications, the most prominent of which you could say is generation of X-rays. Thermionic emission is used to generate X-rays. You will study this in detail in later modules. Right. Next, let's also discuss photoelectric effect. Now we have already briefly talked about this in the chapter light. We had discussed this under the heading where we saw that light sometimes behaves as a wave and sometimes it behaves like a particle. Now photoelectric effect is an example where light behaves like a particle. Now recall the animation that we had seen to understand photoelectric effect. Once again you see that light is falling on a metal surface. Now we have already seen that metal have free electron. Now as this light falls, this light provides the required work function, the required kinetic energy to jump out of the surface. Now, once the electron jumps out, the applied potential difference facilitates its movement from one terminal to the other terminal. And due to its motion, a current starts to flow. This current that flows is called the photoelectric current. Now, in this case, if you think about it, the energy that is needed to eject that electron is being provided by light. Now, light is a wave and it carries an energy which is given by the expression hc by lambda, where h is called the Planck's constant. So in photoelectric effect, light actually behaves like a particle. It carries discrete amount of energy given by this expression. So you could say that light is small packets of energy where each packet has the amount of energy given by this expression. So these electrons which are on the surface of the metal are being bombarded by these packets of energy. And at a time, they can only receive one packet. This is why we had already discussed that light of smaller frequency cannot eject electrons. But if the frequency is high enough, which means the wavelength which is in the denominator is low enough, then the packet would have sufficient energy to make that electron jump out. Right. So, we discussed that metals have free electrons, and these free electrons are electrons which are out of their valence shell because their interaction with the nucleus is not very strong. Then we saw that the minimum energy required to eject such an electron out of the surface is called its work function. Then we realized that this energy that is needed to eject an electron can come from various sources. If the energy needed comes through heating, then the phenomena is called thermionic emission. On the other hand, if the same energy is provided by the light falling on the metal surface, then the phenomena is photoelectric effect. In the next lecture, we will discuss about cathode rays. Thank you.